welcome to Veteach. Now I am going to explain this last unit, 5th unit, design of machine tools. So the contents what I am going to discuss in this particular unit is introduction, classification of levers, design of lever, foot lever, crank lever, design of lever loaded safety valve, wire ropes designation, stresses and design procedure, all these things I am going to cover. You can see this. So this is a beam and there is a fulcrum here, and you want to lift up a load. In order to lift up this load, you are applying the effort here. So this is, we are going to study about the levers. This is a lever. This is a lever. So this is a simple figure or example of this lever. We'll see that in detail. Introduction to levers. Lever is a rigid rod or bar capable of turning about a fixed point called fulcrum. It is used as a machine to lift a load by application of small effort. So lever is basically, it is a rigid rod or bar. So this is the lever. So this is being operated about a fixed point. So fixed point means this is the point about which it is just turning. So about this is it can be moved like this. It is moved about this point. This is called fulcrum. It is used as a machine to lift a load by application of small effort. You want to lift up more load and you want to apply a less effort. By applying less effort because of this length, so weight is having shorter length and this effort is applied at a larger length. So thereby, if you apply the force, this turning moment, whatever the force, turning moment is, if this effort is P into L. So more the length, the effort will be less for the same torque. If the length is more, the effort, length is increased, means effort is reduced for the same torque. By having this mechanical advantage, you can lift up more load with the help of the less effort. That is the advantage of the lever. Ratio of load lifted to the effort applied is called mechanical advantage. Mechanical advantage is equal to load lifted by effort applied. So this is the load lifted and this is the effort applied. You can see this in this diagram. So fulcrum, this point B is the point of application of the effort. This is effort. And you want to apply this load. This is the load. So this load is acting through point A. This load is, effort is applied at point B. And this particular lever is operated like this about this fulcrum. This is operated about this fulcrum like this. So if you see if you take moments about this fulcrum, this W into L1, this is the turn moment, and P into L2, P into L2, P into L2. So W by P is equal to L2 by L1. W by P mechanical advantage is L2 by L1. So by having more length L2, you will have more mechanical advantage. I'll repeat this. By having more length L on effort side, you will have more mechanical advantage. You see this. The ratio of effort arm L to the load arm L1 is called leverage. So this L2 by L1 is called leverage. More the leverage, more is the mechanical advantage. So that is the purpose of this lever. A simple component is used as a machine to lift up large amount of load with the help of a small effort. Now you can see the classification of levers. You can see this. So class 1 lever, the hallmark of this class 1 lever is fulcrum is in between the effort and load. Just now I explained about this class 1 lever only. Class 2 lever is the load is in between the fulcrum and effort. Load is in between the fulcrum and effort. You can see this. This is the fulcrum and this is the effort. And class 3 lever is, you can see this. The effort is in between the fulcrum and load. Effort is in between fulcrum and load. Class 3 lever. So you can see the free body diagrams here. So about the fulcrum, for example, if this is the fulcrum here for this figure. So you have a reaction, support reaction RF. RF is the reaction at the fulcrum. P is the effort applied, W is the load raised. You can see RF here, W and P. You can see RF there. You see, here you have to understand something. RF is acting in upward direction in both the occasions, whereas you can notice this RF is acting down. Here load is acting down and effort is applied upwards, and this is acting downwards, because effort is applied upwards, this is acting downwards. Okay, you can see the examples here for class 1 levers, bell cranked levers used in railway arrangements. So this is the bell cranked lever. Rocker arm in IC engines, handle of a hand pumps, hand pump. You can see the hand pump there like this. Foot lever, hand wheel or punch press. Okay, these are all the examples of class 1 levers. And if you see the class 2 levers here, so levers of loaded safety valve. So in a pump, hand pump, what happens is you have a lever like this. So you have a fulcrum here. This is the fulcrum. And if you apply the effort here, load is raised here. So this is where, and you have a piston here inside. You can get the water out. Okay. So this is the handle of a hand pump's class 1 lever. Whereas this is the lever of a loaded safety valve. So here you have the, you can see this, the fulcrum is at the end. You can notice this here. Now pairs of tongues, the handles of a seeing machine, you can see them in clear picture. You can see this here. This slide will show you a clear understanding. Class 1 levers, you can see this here, load, fulcrum, effort. What you are doing is you are opening this particular one, and class 1 lever, scissors, you can see this is the fulcrum. You are applying the effort here. So this is coming close, load. So something you want to cut. So this is where it is loaded. Now this is the class 1 lever. And you can see the class 2 lever here. So you can see the trolley here. So this is the fulcrum and this is the load, this is the effort. You can see the tongs. Okay, something you want to put, hold or something. So this is class 2. You can see the car door. So this is where the fulcrum is. About this it is opened and closed. And you are applying the effort here. And load is whatever the door that is there, that is the door is the load. Load is in between the effort and fulcrum. Car door is an example of class 2 lever. Now class 3. So fulcrum and effort is in between the load and fulcrum. So fulcrum is your hand. If you want to this particular one, fulcrum is in your hand and you are applying the effort in between, and this is moved, this is cleaned here like this. This is where it is loaded. You will clean it like this. And these are all the examples. You can see this here. Okay. So class 1, class 2, class 3 levers. These are the different applications of the class 1, class 2, class 3 levers. Now let us see the design of these levers. We will focus on the design part of the lever. Design of a lever consists in determining the physical dimensions of a lever when forces acting on the lever. Of course, design is all about finalizing the dimensions. Forces acting on the lever, load which is to be raised, and effort and reaction at the fulcrum. Okay. So find the reaction at the fulcrum like this. So if you see the class 1 lever like this, so RF is acting upwards, weight is acting down, P is acting down, RF you will calculate like this. So for class 2 levers, RF like this, for class 3 levers, RF like this, and a lever shape is like this. You see this is the fulcrum. So this is inclined and this is horizontal. You will have the RF like this. So here this is vertical, this is horizontal. So this is called effort arm. This is called effort arm. So this is called load arm. Effort arm is vertical and load arm is horizontal. You have the RF like this. RF means reaction at the fulcrum. So you see this effort arm is inclined, load arm is horizontal. You have it like this. So this is the way you calculate the reaction at the fulcrum. Now you see this. In the case of levers having two arms as shown in figure, cranked levers, the maximum bending moment occurs at the boss. You see this here. You can notice this lever. So this is the fulcrum. Fulcrum is, this is where you have a turning pair. About this fulcrum, this is moving like this. So this is called boss. So this is the fulcrum pin, and your weight is here and your effort is here. This is the lever. So this lever can have, you see, the maximum bending moment occurs at the boss. Because of this force bending moment is occurred at the boss. You see this, you can see this. The maximum bending moment occurs at the boss. So this is called boss. This is where it is subjected to maximum bending moment. So this force multiplied by perpendicular distance, or this force multiplied by perpendicular distance. And you have different cross sections for the levers. You have a rectangular cross section. Of course, it is subjected to bending. You know, bending stress is M by Z. So bending moment by section modulus. Z is equal to I by Y. So I by Y. It is for the rectangular section 1 by 6 TH square. So Z is equal to I by Y. I is TH cube dimensions. So you can make this assumption. Major axis is taken as 2 times to 2.5 times of the minor axis. For I section, you see this Z flange area into depth of the section. For I section modulus is, you know how to find out the section modulus for the I section. So this is something I already discussed here. The dimensions are already in my previous discussions. I discussed about, while discussing about the connecting rod, I discussed about this Z section modulus in detail. Clearly I explained about this in the design of connecting rod. The dimensions of fulcrum pin are obtained from bearing considerations. You see this. So fulcrum pin. So this is something subjected to bearing pressure. This pin is designed for bearing pressure. And then check for shear stress. The length of pin can be taken as 1 to 1.25 times of the diameter of the pin. The diameter of the boss is taken as twice the diameter of the length of the boss. So I conclude it now. Thank you.